Welcome to the first lesson of our theoretical physics series. Today we'll explore the fundamental concepts of speed, velocity, and acceleration. Here is an example. Two cars can both say they are moving at 60 kilometers per hour, yet one of them may be changing its motion while the other is not. A car turning in a circle can accelerate if its speed never changes. Another example is when I throw a ball straight up. There is an instant when its velocity becomes zero, but its acceleration does not. From these two examples, we can give out the question to ourselves to ask if, so, what exactly do physicists mean by motion? If you want to understand about mechanics, astrophysics, relativity, even quantum particles later on, you need to get these first ideas completely right. Today, we start with the most basic language of motion: speed, velocity, and acceleration. In everyday life, we often use speed and velocity as if they mean the same thing. For example, the speedometer in our vehicles shows how fast our cars or bikes are moving. However, in physics, they are not the same. We also tend to think that acceleration simply means going faster. But in physics, that is only part of the story. In this video, we will build the correct framework from the ground up. We will answer 5 questions. What is motion? What is the difference between distance and displacement? What is the difference between speed and velocity? What is acceleration really? How do graphs describe motion? By the end, you should be able to look at a moving object and think like a physicist. Part 1. What is motion? Let's begin with a deceptively deep question. What does it mean for something to move? At first, this may sound trivial. We might say that something moves when it changes its position. However, this immediately raises an important issue. Changes in position relative to what? That relative to what is essential. For example, if you are sitting inside a smoothly moving train, the person next to you appears stationary. But to someone standing on the platform, both of you are moving at high speed. This shows that motion is not defined absolutely in ordinary mechanics. Instead, motion is described relative to a reference frame. This leads us to our first key idea. Physics describes motion by tracking how an object's position changes over time relative to a chosen frame. So whenever we talk about motion, we are really referring to 3 fundamental elements: position, which indicates where an object is located; time, which measures the duration of an action or movement; and a reference frame, which is an abstract coordinate system defined in physical space. These 3 components form the underlying structure for everything that follows. Part 2. Distance versus displacement. Now let's make our first major distinction: distance and displacement. These two are not the same. Imagine a runner completing exactly 1 lap around a circular track and ending at the starting point. The question is, how much distance did they travel? The answer is the full length of the track. But what about displacement? In this case, the displacement is 0, because displacement does not measure the total path traveled. Instead, it measures the change in position from the starting point to the ending point. Distance is a scalar quantity, meaning it has only magnitude. Displacement, on the other hand, is a vector quantity, which means it has both magnitude and direction. Displacement depends on where you started, where you ended, and the direction of the change between those 2 points. In simple terms, distance asks, how much ground did you cover? Displacement asks, where did you end up relative to where you began? Let's consider a simple one-dimensional example. Suppose you walk 3 meters to the right and then 2 meters to the left. Your total distance traveled is 5 meters, calculated by adding 3 and 2. However, your displacement is only 1 meter to the right, calculated as plus 3 minus 2. This difference highlights why direction is so important in physics. The world does not only care about how much motion occurred, but also how that motion changed position in space. Why displacement matters? Displacement is often more physically meaningful than distance. Why is that? Because many physical laws depend on direction. Force has direction, velocity has direction, momentum has direction, and even electric fields have direction. This means that direction is not just an extra detail, it is fundamental to how physics describes the world. So even in this first lesson, we are already moving away from casual everyday language and toward the precise language of physics, the language of vectors. Part 3. Speed versus velocity. Now we arrive at another crucial distinction in physics, the difference between speed and velocity. Speed describes how fast something moves, regardless of direction. Because it only has magnitude, speed is classified as a scalar quantity. Velocity, on the other hand, describes how fast something moves together with its direction. Since it includes both magnitude and direction, velocity is a vector quantity. Let's first discuss average speed. Average speed is defined as the total distance traveled divided by the total elapsed time. We have an example here. If a car travels 100 kilometers in 2 hours, then we get the average speed for a car. Average speed equals total distance divided by total time, which equals 100 divided by 2, which equals 50 kilometers per hour. So the average speed of the car is 50 kilometers per hour. This idea seems simple, but things become more interesting when we discuss average velocity. Average velocity is defined as displacement divided by elapsed time. Average velocity equals change in position divided by change in time. Another example for this case. Imagine we have a car, drive 60 kilometers to the north, then 60 kilometers to the south, returning where it started with 2 hours elapsed. Then we have the average speed. Average speed equals total distance divided by total time, which equals 60 plus 60 divided by 2, which equals 60 kilometers per hour. However, the displacement in this situation is 0 because the car ends exactly where it started. Therefore, the average velocity becomes average velocity equals delta x divided by delta t, which equals 60 minus 60 divided by 2, which equals 0. It is 0 in this case because the car moved the same distance, but in reverse, so the displacement is 0. The average velocity is tied to the displacement, so indeed, the average velocity is 0. In physics, velocity can also be negative. In one-dimensional motion, we usually assign a sign convention where motion to the right is positive and motion to the left is negative. For example, a velocity of plus 5 kilometers per hour means motion toward the right, while minus 5 kilometers per hour means motion toward the left. The negative sign does not mean the object is moving more slowly, it simply indicates direction. This idea becomes extremely important in more advanced areas of mechanics. Part 4. Instantaneous motion. Average quantities are useful for describing motion over a period of time, but real motion is constantly changing. A car may move faster, slower, stop, turn, or accelerate at different moments. Because of this, physicists often care about motion at a single instant in time. This idea is called instantaneous velocity. Instantaneous velocity describes how fast an object is moving and in which direction at a specific moment. A common everyday example is the speedometer in a vehicle. The value shown on the speedometer tells you how fast the vehicle is moving at that exact moment, rather than over the entire trip. To describe instantaneous motion more precisely, physicists naturally connect this idea to calculus. In mathematics, instantaneous velocity is related to the slope of a position versus time graph at a particular point. The steeper the slope, the greater the velocity. For now, we do not need to go deeply into the mathematics. It is enough to understand that instantaneous velocity describes motion at a precise moment in time. Part 5. Acceleration, and what's special about it. Now we arrive at one of the most misunderstood concepts in basic physics: acceleration. Many people think acceleration simply means speeding up, but that is only part of the story. In physics, acceleration means a change in velocity over time. Since velocity includes both speed and direction, acceleration occurs whenever speed increases, speed decreases, or direction changes. Mathematically, acceleration is defined as the change in velocity divided by the change in time. This means acceleration is not only about speeding up, it can also describe slowing down or changing direction. In other words, acceleration measures how velocity changes over time. Let's begin with a simple example of speeding up. Suppose a car increases its velocity from 0 to 20 meters per second in 5 seconds. The acceleration is calculated as acceleration equals delta v divided by delta t, which equals v2 minus v1 divided by t2 minus t1, which equals 20 divided by 5, which equals 4 meters per second squared. This means the car's velocity increases by 4 meters per second every second, assuming the acceleration remains constant. Now consider an example of slowing down. Imagine a car moving at 20 meters per second that comes to rest in 5 seconds. The acceleration becomes acceleration equals delta v divided by delta t, which equals v2 minus v1 divided by t2 minus t1, which equals 0 minus 20 divided by 5, which equals negative 4 meters per second squared. The negative sign indicates that the velocity is changing in the direction opposite to the chosen positive axis. In everyday language, we often call this deceleration, but in physics, it is still considered acceleration. Specifically, negative acceleration within a chosen coordinate system. Acceleration can also occur even when speed remains constant. Imagine a car moving in a circle at a constant speed. Although the speed does not change, the direction changes continuously. Since velocity depends on both speed and direction, the velocity is constantly changing. Therefore, the car is accelerating. This is why circular motion always involves acceleration, even at constant speed. Another classic example is a ball thrown straight upward. As the ball rises, its upward velocity becomes smaller and smaller until, for a brief instant at the top, the velocity becomes 0. Many people mistakenly think the acceleration must also become 0 at that moment. But that is not true. Gravity is still acting on the ball the entire time, so the acceleration remains directed downward near Earth's surface. G is approximately 9.8 meters per second squared, so even if the velocity becomes 0 now, acceleration can still be non-zero. The velocity tells you what motion is happening. Acceleration tells you how motion is changing. These are different types. Part 6. Constant acceleration formulas. Equation proving. When acceleration is constant, there are few equations that becomes useful. The first definition of acceleration rearranged. V equals v naught plus at. This equation tells us that the final velocity equals the initial velocity plus acceleration multiplied by time. It describes how velocity changes steadily when acceleration remains constant. If position is also important, we can use another equation. X equals x naught plus v naught t plus 1/2 at squared. This equation shows how an object's position changes over time under constant acceleration. The first term represents the initial position, the second term represents motion due to the initial velocity, and the final term represents the additional effect of acceleration over time. There is also a useful relationship for average velocity under constant acceleration. V sub average equals v naught plus v divided by 2. In fact, these are not random formulas to memorize blindly. Each one is telling a physical story, where either velocity changes steadily by time, position accumulates from motion over time, acceleration shapes the curve of motion. We will derive them and use them more deeply later. But for now, these are compact summaries of how constant acceleration works. Part 7. Motion graphs. Position versus time graph. A position time graph helps us understand how an object's position changes as time passes. When we look at a flat horizontal line on the graph, we can see that the position does not change over time. This means the velocity is 0, so the object is at rest and not moving at all. When the graph becomes a straight line with a constant slope, it shows that the object's position is changing by the same amount every second. This indicates a constant velocity, meaning the object is moving steadily in one direction. If the line is steeper, the slope is greater, which means the object is moving faster. In other words, a steeper slope represents a greater speed. Finally, when the graph is curved instead of straight, the slope is constantly changing. This tells us that the velocity is also changing, which means the object is accelerating. In this case, the motion is not uniform and the speed is not constant. This type of graph is often more realistic because in real life, Objects rarely move at perfectly constant speeds for long periods of time. Velocity versus time graph. One of the best ways to understand motion is through graphs. A velocity time graph shows how the velocity of an object changes over time, allowing us to see not only how fast the object is moving, but also how its motion evolves. In this type of graph, the slope is especially important because it represents acceleration. If the graph is a flat horizontal line, it means the velocity is constant and the acceleration is zero. When the graph slopes upward, the velocity increases with time, indicating positive acceleration. On the other hand, if the graph slopes downward, the velocity decreases, which corresponds to negative acceleration. Another powerful idea in velocity time graphs is the meaning of the area under the curve. The area between the graph and the time axis represents the displacement of the object. This shows that graphs are not just visual tools, but compact ways of expressing physical relationships. By interpreting both slope and area, we can extract detailed information about motion. This connects naturally to acceleration time graphs, which describe how acceleration changes over time. When acceleration is constant, the graph appears as a flat line. Similar to velocity time graphs, the area under an acceleration time graph represents the change in velocity. Altogether, these relationships form an important chain in mechanics. Changes in position produce velocity, and changes in velocity produce acceleration. This layered structure is fundamental for understanding motion in physics. Part 8. Worked examples. Example 1. Runner. A runner completes a lap of 400-meter circular track in 80 seconds. What is the average speed? 400 divided by 80 equals 5 meters per second. What is the average velocity? The displacement after a full lap is 0, so the average velocity is 0. Same motion, but two different answers. Two concepts are different. Example 2. Car accelerating. A car increases its velocity from 10 mph to 25 mph in 3 seconds. The acceleration is acceleration equals delta v over delta t equals v2 minus v1 over t2 minus t1 equals 25 minus 10 over 3 equals 5 meters per second squared. It means that velocity of the car increases 5 meters per second every second. Example 3. Ball thrown upward. A ball is thrown upward. It means that at the top of the motion, velocity is 0, and the acceleration is still downward. As the speed decreases when the ball is thrown upward, fly upward. That's one of the most important aspects in basic mechanics. Zero velocity doesn't mean zero acceleration. Example 4. Turning car. A car is moving at constant speed, then it bends. The question we would ask here is that, is it accelerating still? The answer is yes. Because the velocity is changing, acceleration still exists. Part 9. The bigger idea. The idea seems simple, but these principles are the key to most of physics. Newton's laws become most meaningful when velocity and acceleration are defined with precision. Momentum depends on velocity, while kinetic energy depends on speed. Orbital mechanics rely on the continuous change in velocity. Relativistic mechanics reshape how motion is measured at extreme speeds, and quantum mechanics redefine particles altogether when motion becomes probabilistic. Part 10. Recap. To summarize all of this, we need to look at the lesson today we have learnt so far. Motion is the measured relative to the reference frame, helping us to understand what's about things and other when it moves. Distance is total path length. Displacement is change in position. Then we also have speed and velocity. These two describe how fast something moves, but velocity is dependent on how the object moves in which direction, set by reference frame. Also, average speed and average velocity, being calculated from distance and displacement respectively. Acceleration also depends on velocity and how it changes over time. Moreover, the graph is being told for us to see how the speed increases or decreases. Direction changes. These graphs let us see these ideas more visually for the slope of position time, velocity, velocity time, acceleration, or even the area under velocity time for displacement. That's it for today. If you enjoyed this journey through physics, hit like, subscribe, and we'll see you in the next one.